In this video, we are going to compute the improper integral from negative infinity to infinity of x squared divided by x squared plus 25, that quantity squared. We're going to compute this using residue calculus. So the first thing I'm going to do is set up a function, which is a function of the complex variable z. So while the integrand function here is a function of a real variable, let's let f of z be z squared divided by z squared plus 25 squared. In order to use residue calculus to evaluate this integral, we need to know where this function has singularities. So let me take the denominator and rewrite that first as z squared minus negative 25, all of that squared. We can factor z squared minus negative 25 using difference of squares factoring, and then each of those individual factors will get squared. So the end result is z squared all over z minus 5i squared z plus 5i squared. So f has poles at 5i and negative 5i, and each is order 2. All right, next let's create a contour that we can use to evaluate this integral. This is going to be a contour in the complex plane. And as we typically do with this kind of computation, what we're going to say is that our integral from negative infinity to infinity is going to be like going along an interval like this, where I'm going to say that this number is negative rho and this is positive rho. And then because we need to close this off into a contour, let's go along the upper semicircle of radius rho. I'm going to name this contour gamma sub rho. And the upper semicircle I'll call C subscript rho, and it's the upper semicircle, so that's just my notation for that. As a preview, what will happen is that the component along the real axis as rho goes to infinity will give us the value of our integral, whereas the evaluation along the upper semicircle is going to vanish as rho goes to infinity, so that ultimately going around this contour is really just like going along the real axis, but using residue calculus, we can evaluate the integral around the contour. So that's the idea. As we want to imagine that the radius rho is going to go to infinity, we are going to be enclosing the singularity at 5i. So we need to compute the residue at 5i. All right, since the singularity at 5i is a second order singularity, what we can say is that the residue of this function at 5i is the limit as z approaches 5i of the first derivative of the product of z minus 5i squared times f of z. So we have to do that. Okay, so we're going to take the limit as z approaches 5i of the derivative of z squared divided by z plus 5i squared. So there I use the factored form of the denominator that we had a minute ago. So that will be the limit as z approaches 5i. I think it's going to be easier to differentiate z over z plus 5i, that fraction squared. Just think that's going to look a little bit nicer. So that will be the limit as z approaches 5i. Using the chain rule, we're going to have 2 times z over z plus 5i to the first power times, with the quotient rule, we'll have low d high, so that's going to be z plus 5i minus high d low, so that's going to be minus c all over low low. All right, z's cancel out. Now let's go ahead and take this limit. That will be 2 times 5i over 5i plus 5i, so that's 10i, times 5i again over 10i, that quantity squared, so that's 100i squared. Okay, the final result over here to the right. Let's see, we can cancel out I squareds. Let's see, 2 times 5 is 50 over 100 is going to be a half, but times 1/10 is 1 over 20. And then I will leave the remaining I in the denominator because it will cancel nicely when we evaluate the integral. All right, so let's say the integral from negative infinity to infinity of x squared over the quantity x squared plus 25, that squared, dx, is going to be the limit as our radius grows to infinity of the integral around the closed contour of z squared over z squared plus 25 squared. Take away the upper semicircle. That will be the limit as the radius grows to infinity of the integral along the upper arc of z squared over z squared plus 25 squared. All right, since our closed contour encloses the pole at 5i, we can say that the first integral is 2 pi I times 1 over 20i. And then as the radius grows to infinity, the second integral vanishes. So I'll write minus 0, where that result is because the degree of the denominator is 4 and the degree of the numerator is 2. So the degree of the denominator is at least 2 larger than the degree of the numerator. So now we conclude that the integral of this function from negative infinity to infinity is going to be pi over 10. You'll notice 10 looks like a multiple of 5, which we squared to get to 25, so let's just generalize this result. So here's a more general expression where we imagine that a here is some non-zero real number. You can repeat these steps to conclude that this integral, written in terms of a, will be pi over 2a. So in our example, a was 5, and we got pi over 10. And then since this function has even symmetry, if I was only interested in evaluating the integral from 0 to infinity, we would just cut that number in half. So that result would be pi over 4a. All right, that wraps up our example. Thank you for your attention.